Hey guys, it's Margot at Lanterna. Today we're going to be looking at the second part of our discussion of vectors for the analysis and approaches syllabus. And we're going to cover the cross product and the equations of a plane. And this falls under parts 3.16 to 3.17 of the higher level syllabus. So first of all, the cross or the vector product. Now in the last video, we outlined that unlike scalars, there's no one way in which we can multiply two vectors together. So in the last video, we looked at the scalar or dot product, which took two vectors and multiplied them in such a way that out came a scalar. Now we're looking at the cross product or the vector product, and the name already gives it away. We're taking two vectors, multiplying them together in a way that we get another vector. Now, we have an equation for this. It's not as nice as the equation for the scalar product, but it's given in our formula booklet, and each component is given by taking a component of the first vector, multiplying it by a different component of the second vector, and subtracting it by the reversal of that, essentially. Now, there's a lot of numbers in this formula, so be careful when you're using it to pay really close attention to which component you're multiplying by which one and subtracting it from what. So let's learn a little bit more about this. As we said, the product is a vector quantity. Now you might ask yourself, if it's a vector, okay, well, we get the magnitude of each component using this formula, but can we visualize its direction? Well, the vector product actually computes a vector which is perpendicular to the two vectors which we're multiplying, and the direction of that vector is given by the right-hand rule. So if we look at this diagram here, take for example two vectors A and B. If we multiply them using the cross product, well, that vector C is going to be perpendicular to those two vectors. Now the question is then, does that perpendicular vector point up or does it point down? And that's what the right-hand rule tells us. What we have to do is we take our right hand and we curl our fingers from vector A to vector B, and in the direction that our thumb points is the direction of the cross product. So in this case, it's up, as we've shown in the diagram. Another property which we need to bear in mind, we're going to have a little look at it in more detail in the next slide, is this one here, is that the magnitude of the cross product is equal to the magnitude of vector V times the magnitude of vector W times sine theta, where again, theta is the angle between our two vectors. So some properties of the cross product. These properties that we're going to list in this slide are not given in the formula booklet, but it's really important that you know them. And the best way to do that is to really understand them. And with vectors, understanding often comes with being able to visualize it. So let's look at the first of these properties, V cross W. If we have V cross W, if we visualize what that cross product is, well, we have a vector V here, and we multiply it by, we'll take the cross product with a vector W there. Then, as in the last slide, we said that the cross product of those two vectors, V cross W, is going to give us a vector which is perpendicular to both of those. And it's in the direction shown here, V cross W. Using the right-hand rule, curling our vectors from V around to W gives us a vector that points up. Now, if we take it the other way around, we do W cross V, we now need to curl our fingers in the opposite direction. So with V cross W, turn them in an anti-clockwise direction, but now we have to go in a clockwise direction to get from W to V. And in that case, our thumb is now pointing down, and therefore our vector W cross V is in the opposite direction of V cross W. And remember, the opposite direction with vectors is denoted by a negative sign. So hence V cross W is equal to the negative of W cross V because they are in opposite directions. The next property then, V cross V is 0. Well, if we think about what V cross V is, we're taking a vector, V, and we want to find a vector which is perpendicular to V and V. Well, V and V are parallel, and therefore there's not really such a thing as a vector which is perpendicular to these two. There's no one direction we can think of which is going to give us explicitly a vector perpendicular to V. And how do we summarize that? Well, we say then V cross V is 0. Next one then, U cross V plus or minus W. Well, we can just expand that as we would intuitively expect we can. Finally then, the dot product of U with the cross product of U cross W. Now, if we have a vector U and we have a vector W, then as we've said before, our vector U cross W is going to look something like this. It's going to be perpendicular to both our vectors, which means that the angle between our vector U cross W and U is 90 degrees. And if we remember from the dot product, remember we said A dotted with B was equal to the magnitude of A times the magnitude of B cos of theta, from which we deduce that for two perpendicular vectors, when theta is 90 degrees, the dot product is 0. So if we take U dotted with U cross W, we see if we represent these vectors in a 3D plane that is going to give us 0. Good. So we had an equation on the previous slide, which I said we're going to pay a little bit more attention to here. And that is the equation of the magnitude of V cross W. If we take the magnitude of V cross W, we know it's equal to the magnitude of V times the magnitude of W times sine of theta. Well, if we imagine these vectors V and W in space, and what therefore the magnitude of their cross product represents, if we look at this diagram here, we can convince ourselves that the magnitude of V cross W is actually equal to the area of a parallelogram, because we can represent V sine of theta as this vertical length, and therefore if we multiply it by W, which is the length of the horizontal side, we find the area of our parallelogram. Now, that's important to remember, and it's also important to remember what we can deduce from that, which is that the area of a triangle with sides V and W is therefore half of this magnitude. If we had a triangle with lengths V and W, then we can draw this triangle as follows. We've got length V and we've got length W, and the angle between them is theta. So this red triangle is what we're intending to find the area of here, and we see that that is exactly half the area of this parallelogram. So therefore the area of a triangle is equal to half times the magnitude of V cross W. Now that's a really important application to remember. They don't give you that formula in the formula booklet, but they will often ask you to find the area of a triangle when you have information regarding vectors. Now, in that case, you can go to use some of your triangle trigonometry rules, but that would take a lot more work than this really nice formula we've got here. So moving on then to the equations of a plane. Now there's a number of different ways in which we can represent the equation of a plane. And the first one we're going to have a look at is this vector equation of a plane, which we've got on the slide right here. And what we're going to do is, just like with a vector equation of a line, we're going to take each of these components of the equation and really understand what they mean, and therefore see how we combine them in this equation and why that describes the equation of a plane. What we're going to do after that is derive another form of the equation of a plane, which is the Cartesian form. So first of all, let's look at these components in the vector equation of a plane. So first of all, n. N is the normal vector to the plane. What that means, a normal vector is a vector which is perpendicular to the surface. So we can indicate it right here, this vector n, we see it points away from the surface and is perpendicular to it. The second vector then, r, similarly to what R represented for the vector equation of a line, here R represents the position vector which takes us from the origin to any point on our plane. So in this case, we've denoted a general point on our plane as point P, and this vector r takes us from the origin to any of those points on our plane. R0 is the position vector of a point P0 on the plane. So R0 is the position vector which takes us from the origin to a point on the plane which we know lies on the plane. So how then does this equation describe the equation of a plane right here? Well, first of all, let's have a look at what R minus R0 is. Well, just as we've shown on the diagram right here, R minus R0, so what we'd be doing is we'd be following negative R0, so going in the opposite direction to R0, i.e. going from the point P0 to the origin, and then adding our vector R, which takes us to point P, so that overall R minus R0 takes us from P0 to our point on the line, which means that R minus R0 is a vector which lies on our plane or in our plane. So let's make a note of that. This is a vector which lies on the plane. R minus R0 is a vector which lies on the plane. Now, if we take the dot product then with a normal vector, well, the normal vector is perpendicular to the plane. Therefore, the normal vector is perpendicular to R minus R0, and therefore their dot product must be equal to 0. So that is the equation of a plane. And now we've deciphered all those components, we can see why that equation makes sense. Any line in the plane must always be perpendicular to the normal of the plane. Good. So let's have a look then. How can we transform this vector equation of a plane and instead get the Cartesian form of the equation of a plane? Well, in order to do that, we're going to say a little bit more about these vector components. So first of all, the normal to the plane, we're going to say has an x coordinate, an x component A, a y component B, and a z component of C. Second of all, we're going to say that R0, which is the coordinates of a point on the line, let's say that has arbitrary coordinates x0, y0, and z0. Then R, which is the vector equation of a line to a point P on the plane, well, we want to be able to describe any point with any coordinates. So we're going to give this some arbitrary coordinates x, y, z. So what we know here is the components of our normal, and we know a point on the line, and we're trying to describe this set of coordinates x, y, z, which describes all the points on the plane. So if we fill these vectors now into that vector equation of a plane, then we're going to get something that looks as follows. We're going to have vector A, B, C, dotted with x minus x0, y minus y0, z minus z0 is equal to 0 according to our vector equation of a plane. Now, if we compute the dot product, so we'll get something that looks like this. We'll get a x minus a x0. So what I've done there, I've already just expanded that x minus x0 bracket, plus by minus by0 plus cz minus cz. cz0 is equal to 0. So that is the next stage of our conversion from our vector form to our Cartesian form. Okay, so we said before that we know what the A, B, and C components are, and we know what this coordinate x0, y0, and z0 is. And what we want to find is the set of coordinates x, y, z, which are the points which lie on our plane. So what we're going to do is on the left-hand side of this equation, we're going to keep all our terms which include those coordinates of any point on the plane, so our x, y, z, and to the right hand side we're going to move all the terms, which we essentially can calculate if we know the point on a plane. So what we get then is ax plus by plus cz is equal to ax0 plus by0 plus cz0. And now what we say for simplicity is, because we know the value of all of these things here, they're just constants multiplied by each other, we just give that another name and we say that that is equal to some constant d. So what's the most important thing to know about the Cartesian form? Well, it's that a, b, and c, which are the coefficients of our x, y, and z, which are the coordinates describing any point on our plane, a, b, and c are the x, y, and z components of the normal of the plane. So if we get given the equation of a plane in Cartesian form, then we can straight away extract from that the vector equation of the normal. So that's really important to be able to pick out there. And what's also important is how we converted from the vector equation to the Cartesian form. So I really hope you enjoyed this video today, guys. I really hope you found it useful. I'm going to be back with more videos later, but in the meantime, check out some of our other videos from other great tutors in subjects such as chemistry or economics or ESS or geography. You can find those on our website or on our YouTube page. I hope to see you next time.